Let's look at some random AP Precalculus problems from section 1.1. We have ourselves a graph, okay, a little going down, a little going up, and we have some questions about said graph, so let's answer those questions. On which interval is the graph concave up? Concave up looks like this. So our concave up starts here, still concave up, 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 and this is right about where it changes. So what we'll say is negative infinity. Now that parentheses means you don't include it, and you wouldn't include negative infinity anyway. It's a concept. And it goes all the way to 0. Now we're not going to make a bracket. We're going to make a parentheses because at 0 is where it changes. And so the moment it changes, called an inflection point, is neither concave up nor concave down. So no brackets, okay? Just the parentheses, which means you don't include that number. Concave down looks like this. And that goes from 0 all the way to positive infinity. Don't include either of those numbers either. On what intervals is the graph increasing? Now, it's important to understand that graph increasing is not the same as rate of change increasing. That's concave up, concave down stuff. This is just asking, where is the graph going upwards? So this part of the graph is going downwards, and that's going to answer D, so we might as well get it out of the way. At B, it starts going upwards, increasing, and at D, it starts going downwards again. So to answer this question, we will say between B and D is where this is increasing. Now, we're not going to include B, and we're not going to include D, because at B, it goes from decreasing to increasing, and at that very moment, it's a flat slope, which means it's neither increasing nor decreasing. On what intervals is the graph decreasing? Well, we already answered that. From negative infinity to B, and then increasing, and then from D to negative or positive infinity. Now, we're not going to include things, but what we're going to do is, since there's two intervals, we say negative infinity to B, don't include it. This means union. That's when you have more than one interval. And then it's also decreasing from D to positive infinity. Okay? Find the zeros of the function. The zeros are where my line crosses the x-axis. Here at A, here at 0, and here at E. So we will say the zeros are when x is equal to A, when x is equal to 0, and when x is equal to E. And last but not least, find the y-intercept of the function. That's where my line crosses the y or f of x axis. And it looks like since it crosses the origin, the y-intercept is going to be 0. So why not be a little bit specific and say, well, 0, 0, the origin. Okay? Fun. Estimate the rate of change at x equals 1 for the function f of x equals negative 1/2 x squared plus 3x minus 1/2. Now, we know the average rate of change. The average rate of change, the AROC, is going to be f of b minus f of a over b minus a. This isn't asking for that. This is asking for the rate of change at the very moment when x is equal to 1. Well, this involves calculus, and we don't know calculus yet. So we're going to use our calculator to give us a trick. See, we don't know the exact rate of change at 1, but what we could do is we can allow an interval that's awfully close to 1. Like, how about 1 and 1.0001? See, that's not going to give us the actual exact rate of change at 1, but it's going to give us the average between 1 and 1.0001, which last time I checked, 1 and 1.0001 is awfully close to each other. So that's how we're going to handle this. So what I'm going to do is I'm going to run to my calculator. I'm going to find out f of 1.0001 minus f of 1 over 1.0001 minus 1. So let's take a step aside and do that. All right, so the way we're going to handle this is we're going to type in our function right into here. we're going to type out -1/2, so -1 divided by 2. You could do 0.5 if you want. Really, it makes no difference. -1/2 x squared plus 3x minus 1/2. So I'll do 0.5 because, fractions make me nervous. When I take a look at the graph, I'm trying to find the instantaneous rate of change at 1, which means, whatever my slope is at 1 is going to be my guy. And it looks like it could be a +1, +2, +3, but I'm not so sure. So what I did is I set up 1.0001 and 1. So I need to find both of those. So second calc is going to let me find a value at a specific thing. I'm going to use this to find the value of 1.0001 by hitting enter and then typing out 1.0001. Hit enter on that, and that gives me 2.0002. Okay. Now, if you remember from the problem, we said that we're going to do f of 1.0001, which is that, minus f of 1. So what's an easy way of finding out what f of 1 is? Go to second table, and there's f of 1. It's 2. So the equation that I'm going to set up is that f of 1.0001, so let's go back here and set that up, which was 2.0002 minus f of 1, which is 2, all of which divided by 1.0001. So let's throw that into parentheses. 1.0001 minus 1, close parentheses on that, and we get 2. So again, if we were to look at this graph, we can kind of see that at 1, if I were to draw a line there, it might have a slope of 2. Maybe. I don't know. Use your imagination. But that's what we're going to get to Dunzo. All right. So after all of that, we ended up getting what? 2.0001. We ended up getting 2 here. Oh, actually, that was 2.0002, wasn't it? I'm trying to remember what I got. 1.0001 minus 1. When you did the math, you got 2. And so we said 2. And again, I wasn't really able to draw anything on the calculator, but what we saw was a picture that looks like that, a perfect parabola with a bump over here. And so at 1, which we could say that's 1, we had some type of slope, and that slope kind of looked like 2. So that slope is going to be 2. And the rate of change is a fancy word for slope, because doesn't that just look like the slope formula? It does. It should, because it is. What is the average rate of change on the interval from 13 to 25 seconds? Well, you're 13 and you're 25. The average rate of change formula is f of b minus f of a over b minus a. That's the slope formula, boys and girls. So we'll call you A, we'll call you B, which makes you f of A and f of B. And now it's just a matter of plugging stuff in. 30 minus 76, f of B minus f of A, over B, 25, minus A, 13. What was that, negative 46 over 12? Let's see, you could divide the top and the bottom by 2. And that's just about it. So, nothing fancy here, just good old plugging stuff in, and that's that. You're done. Easy peasy. Find the average rate of change on this given interval. Well, we have ourselves a function, and we have the interval -2 to 1. The average rate of change formula is f of b minus f of a over b minus a. So the a and the b are going to be your intervals. So in order to find f of b and f of a, or in our case, w of b and w of a, we're going to have to plug those numbers into that. So let's find w of 1, which involves us plugging in 1. So 5 times 1 squared minus 5 times 1 plus 1 is going to be 5 minus 5 plus 1 is 1. W negative 2, which is my f of a, is going to be 5 times negative 2 squared minus 5 times negative 2 plus 1. So what do we get? 5 times 4 is 20, plus 10, so 30, and plus 1 is 31. 9 plus 10 plus 10. So let's put that all together. Okay, B was f or w of 1. So f of that was 31 minus regular 1 over b minus a, which is 1 minus negative 2. So last time I checked, that's going to be 30. 1 double negative 2 is 3. 30 divided by 3 is 10. So the graph of this is going to look something like that. Okay, and at negative 2 to 1, maybe something like this, okay, you get a slope of 10. Now, this could be the wrong picture. I could be wildly off here, but that's basically what happens. That's going to be negative 2. That's going to be 1. You have a slope of 10. Very steep indeed. The values of a function g are given at selected x values in the table below. The function is either concave up or concave down, but not both. Determine if the function is concave up or concave down. Well, something is concave up if the rate of change is increasing for concave up and decreasing for concave down. So what do? Well, let's find the rate of change. The way you find the rate of change is you go to your table. You make sure that the x values are going up by the same number, which they are. These are called equal length input value intervals. And then you see what's going on here. Okay, so to get from 18 to 20, we add 2. To get from 20 to 20, you add 0. To get from 20 to 18, you subtract 2. And to get from 18 to 14, you subtract 4. Now, whenever we do this, you are finding the rate of change. Because what you're doing is you're finding how g is changing over the course of one step. And you add 2, subtract nothing, subtract 2, subtract 4. The rate of change goes from 2 to 0 to negative 2 to negative 4. Those numbers are decreasing, which means this graph is concave down. Now, if you wanted to, you could probably draw your own picture of this and graph these plots and see that you're going to get something that looks like this. But that's no fun. This is the best way to do it because, you know, it's all pre-calculus-y. Ooh, look at this weird looking unnatural picture. Find the absolute minimum, find the absolute maximum, find the relative minimum and the relative maximum. So the absolute minimum is the smallest point on the graph, which happens to be here. So it looks to me that the absolute minimum is going to occur at the point negative 6, negative 2. Which means my absolute minimum value is negative 2, and that happens at the x value of negative 6. Okay, my absolute maximum doesn't exist because this guy is going to keep going on forever. So there is no absolute maximum. It goes on forever and ever and ever and ever and ever. Now, a relative minimum exists at any point where you basically bottom out anywhere, whether it looks like that, or at this case, could look like that. So that is a relative minimum. So we have several here. We have a relative minimum here, because that's where it bottoms out. Then it goes up, comes back down, bottoms out right there. Goes up, comes back down, bottoms out right there. So we have 3 relative minimums at negative 6, negative 3, and positive 2. My relative maximums are where things go up and peak out, or hit like this. So that happens, it looks like 2 spots, right here, right here. You're not going to include there because that's going on forever, and at no point will it get like the maximum. It's going to keep going. So negative 4 is going to be a relative max, and positive 1 is going to be a relative max. And there you have it. Is there a global maximum or minimum for the function? Now, global maximum or minimum is just fancy talk for absolute, which means is there a spot on a graph where you can't go any higher or can't go any lower? Well, what I have is an 8th degree polynomial with a positive leading coefficient. So I don't know exactly what I have, but if it's an even degree and it's a positive leading coefficient, at one point it's going to start like that and end like that. So at one point, like no matter what we have in between, we are going to bottom out somewhere. It could bottom out at 2 spots, but that doesn't really matter. We are going to have at least a global minimum for a problem like that. So that's basically our answer. The question was not where it happens, not when it happens, but do you have a global maximum or a global minimum? Well, in this case, we're going to have a global minimum just based off of this leading coefficient right there. Find the degree of the polynomial from the given input and output values. All right, so when you're given a set or a table of points, the way you find if something's linear or quadratic is you look for the rate of change, or look for the rate of change of the rate of change, or keep going if you have to. All right, so the way you look for the rate of change is you first make sure that your input values are going up by the same number, and they are. That's called equal length input value intervals. You are making sure that these go up by the same number, they go up by 1, we're in good shape. Now, to test to see if something is linear, you are seeing if this rate of change is the same number throughout. So you figure out what number you add or subtract to get from one number to the next. And if they're all the same, that means the average rate of change is the same and it's linear. You add 1, you add 3, you add 5, you add 7, you add 9, you add 11, you add 13. Is this guy linear? No. So the second time is to test if it's quadratic, and you do it again. You see what you add for every single one to figure out if the average rate of change of the rates of change are the same. And if that's the case, like it looks like it is, 1 to 3 is 2, and 3 to 5 is 2, and 5 to 7, and 7 to 9, and 9 to 11, never forget, and 11 to 13, they're all 2. So my guy, since the rate of change of the rate of change is the same, is quadratic. So find the degree of the polynomial. The degree is 2 because it's a quadratic, baby. F of x equals x squared minus 5x plus 4. When is my function less than or equal to 0? Well, this is what I have. I have a positive leading coefficient quadratic, so I know my graph is going to look like this. What I don't know is what my zeros are. So let's factor this guy out and find out what my zeros are. So two numbers that add up to -5 and multiply out to 4 are going to be -4 and -1, which makes my zeros 4 and 1. So I'm going to make myself a sign chart. Okay, magic happens at 1 and magic happens at 4. I know this picture, when drawn, is going to go through the x-axis at 1 and 4, and I know since this is a positive leading coefficient quadratic, that is going to go like that. Just pretend it's a perfectly straight line, and it's supposed to go where it's supposed to go. Good, no one will ever notice. Now that's what my picture looks like. My picture, when drawn on a coordinate plane, will look like this, go through 1, bottom out somewhere, and go through 4. What do I need to know? I need to know when f of x is less than or equal to 0, which means where is my graph below and touching the x-axis? It touches the x-axis at 1 and including 1, and the reason, again, why we include 1 is we want it to equal 0, so include 1. It stays below the x-axis, negative, between 1 and 4, hits the x-axis again at 4, which means it's a 0, and that's it. So whenever you're asked to do these, you factor out, you find your zeros, you draw a general picture, you answer the question, bada bing. A of x is x times x minus 8, cubed, and x plus 3, to the fourth. We have multiplicity going on here. Now, my multiplicity here is 1, no big deal. My multiplicity here is 3, but most importantly, odd. I'll explain what that means in a second. My multiplicity here is 4, but most importantly, my multiplicity is even. I'll explain that in a second. There's an N there. Now, my degree is found by doing x times 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 x. Why all these x's? Well, if I were to rip all of these apart and write all this out, x times x minus 8 times x minus 8 times x minus 8 times x plus 3 4 times, I would end up foiling out and getting 1, 2, 3, 4, 5, 6, 7, 8 x's. And it's a positive 8 x's because you're positive, you're positive, you're positive. And so the degree of this guy is going to be x to the 8th. Why is that important? Because when I graph that, it's going to start like this, and it's going to end like that. Okay, what's going on in between is found by doing this. What I need to do next is I need to find my zeros. So again, I have x, x minus 8 cubed, and x plus 3 to the fourth. My zeros are 0, positive 8, and negative 3. So let's draw ourselves a sign graph. Magic happens at negative 3, at 0, and at 8. Now, I know the beginning of my graph starts up here. Now, when you're dealing with multiplicity, the first 0 I'm heading towards is negative 3. If your multiplicity is even, your graph does not go through the x-axis. It just shoots right off. Then it peaks out. My multiplicity here is 1, which means it goes through 0. Now I'm going to come back up towards 8. My multiplicity for 8 was odd, so it's going to go through and end like that. Okay, so again, when your multiplicity is odd, like here and here, your line goes through that 0. When it's even like it was for negative 3, it bounces off. I care when a of x is positive and also equal to 0, which means where it's above the x-axis. Okay, now it's above the x-axis from negative infinity all the way to negative 3. Now here's the thing. It hits 0 at negative 3. Am I allowed to include 0? Yes, I am. So my first interval is going to be from negative infinity. It hits 0 at negative 3, so still good, still stays positive, and at 0, it hits 0 and includes 0, so I'm going to include 0. Is that my only spot that it's going to stay positive? Well, right now it's negative, but here it hits 0 again, and then stays positive from 8 and on forever. So we're going to hit union. We're going to include 8 because 8 is allowed to be 0, and we're going to go on forever. So there's my guide. Okay, sign graphs involving multiplicity. So much fun. A polynomial function has 3 real zeros and 4 non-real zeros. One of the real zeros has a multiplicity of 6. Gross. What is the degree of the polynomial? All right, so I have 1 real zero with a multiplicity of 6. So let's simplify this as much as humanly possible. Okay, I have a 0 6 times. I have 2 other zeros, And I have 4 non-real zeros. So z, 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 z. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This has a degree of 12. All right. That's basically it. You just count out how many zeros you have, real and non. And since one of the real zeros has a multiplicity of 6, you count that one 6 times, and then the other 2, and then the 4 that are non. You get 12 total. Don't overthink it. Pretty easy problem. Is each function even, odd, or neither? Well, first things first, an even function when graphed has a mirror reflection over the y-axis. Okay, so is the left and the right exactly the same? When I look at this guy, the left side and the right side are mirror image of each other. You are even. An odd function is, can I take my picture and spin it upside down and get the same exact thing? When I take a look at this guy, although it's not so obvious, if I were to take this picture, spin it upside down, since it goes through 0, 0, and since, you know, I get the same exact thing, it appears that this one is odd. Now, is this even? No, because the left and the right are not mirror images of each other. If I were to take this and spin this upside down, do I get the same exact image? No, I don't. So this is my neither. Is each function even, odd, or neither? A quick way of doing these is if they're even, okay, if it's even, every single variable has to have an even degree. In other words, in x to the 4th, x to the 6th, x to the 0th, which, by the way, is just a regular old constant. That's the even version. The odd version is every single variable has to have an odd variable. So x to the 3rd, x to the invisible 1, x to the 7th. So let's take a look at this. I have 2 terms in w of t. You have an odd exponent, and you have an odd invisible 1. Both of these terms have variables with odd exponents on it. You are an odd function. Take a look at this. We have 1, 2, 3, 4 terms. You are x to the 10th, which is even, x to the 6th, which is even, x squared, which is even, and constant. And again, if it's constant, that means it's x to the 0th, which is even. So you're even. In a case of neither, it was when you would just like mix these two guys up, have a t to the 5th with a t to the 6th, and that would be your neither. Quick way of doing it. Certain values of g of x are given in the table below. Given that g of x is odd, fill in the missing values of the table. Now, the sign of an odd function is this. If I give you g of negative x, you are going to get negative g of x. What does that mean? Well, that means if I were to take negative 5 and make that its opposite, I'm going to get the opposite of this. So g of negative 5, which is g of positive 5, is going to be negative g of x, or negative 10.5. So g of negative 7 is going to be negative 22.5. And u are going to be the opposite of u, which is negative 9. Pretty easy stuff. Describe the end behavior in limit notation. I have myself a polynomial graphed, and what it looks like is happening is this graph going to the left is moving downward, and going to the right is also moving downward. Another way of saying going to the left is the limit as x approaches negative infinity. That means x is heading towards negative infinity, moving to the left. My graph, as I move to the left, is going downward, which means it's heading towards negative infinity. So the limit as my picture moves to the left is going down to negative infinity. That's one side of the end behavior. The other side of the end behavior is if I move to the right. When x gets larger, we say the limit as x approaches positive infinity. And in this case, as x approaches positive infinity, it's also going downward. So as x approaches positive infinity, we are also heading towards negative infinity. Which you're allowed to do. You're allowed to go in the same exact spot both times. That's fine. But this is how you would describe this polynomial in limit notation if we care about its end behavior. Describe the end behavior in limit notation. Well, what I have here is I have a negative 3x to the sixth, and that is my leading term. So two things that we're going to look at. I'm not going to draw this picture as accurately as humanly possible. This is what I know. This is an x to the sixth power. An x to the sixth power is an even degree polynomial, which means the way it opens up is the way it ends. But since this is a negative 3x to the sixth, that means it starts from the bottom, like Drake, and then goes up, makes a few bumps, and ends at the bottom. So I don't know what's happening in the middle here, but who cares? All I know is it looks like that or something like that. That's how it ends. We only care about the end behavior. So the way we write out the left side of the end behavior is as we move to the left, this is going downward. So another way of saying move to the left in limit notation is the limit as x approaches negative infinity. Now we're talking about g of x, so I'll say of g of x. Since we are going downward, as x moves to the left, we're going downward, we are going to say that my limit as x approaches negative infinity of g of x is also negative infinity because we're going down. Just like Fall Out Boy. Remember that song? Very old song. Now, as I move to the right, I'm going to word that as the limit as x approaches positive infinity. And what's happening to g of x as I do that? Well, I'm also going down, which means I'm also heading towards negative infinity. All right, so the trick is you look at your leading term. You look at if it's positive or negative, and you look at if it's even or odd. And since this is even, negative leading coefficient, we go down, both of them are negative infinity. Funzo. Describe the end behavior in limit notation. Well, what I have here is an x to the third is my largest term here, and I have nothing in front of x to the third, which means I have a regular old cubic. Since my leading coefficient is an invisible positive 1, it's going to look something like this. I don't know exactly how it looks, but all I care about is the fact that I have end behavior. And on the left side, as I move to the left, I go down, and as I move to the right, I go up. So how do I write that out? Well, limit as I move to the left is going to be written out as the limit as x approaches negative infinity because x is heading to the left. Cupid shuffle. Now, as I move to the left, I'm also going down. So the limit as x approaches negative infinity of f of x is going down, which means I'm heading down towards negative infinity. As I move to the right, I'm going up. So the limit as x approaches positive infinity, which means x is getting larger, of f of x is going up towards positive infinity. So since I had an odd degree, it ends and starts out different directions. And since in this case, it's a positive leading coefficient, I start from the bottom, just like Drake, and then I end up top, just like me. All right, looks like we have ourselves a gross-looking rational function type thing, and we are being asked to find the end behavior, ask if there's a horizontal asymptote, and then so write out the equation of the horizontal asymptote. Now, it looks to me that we do have a horizontal asymptote, and we do have end behavior, and things seem to level out at this number right here. Okay? Things seem to level out right there. This guy flattens out here. This guy starts down here, comes back up, and starts to flatten out right there. Well, what number is that? That seems to be 4. So what we're going to say is the end behavior of this guy, as x moves to the left, we are approaching 4. Will we ever hit 4 again? Probably not. But as we move to the left, as x approaches negative infinity, we are heading towards 4. As this guy moves to the right, it looks like we're also approaching and probably never hitting 4 as well. Is there a horizontal asymptote? If so, write the equation of the horizontal asymptote. Well, if you're going to level out at a specific number, which I am, that horizontal asymptote is going to be a horizontal line. Horizontal lines are in the form y equals a number, and since that number where things seem to level out is 4, is going to be y equals 4. So is there a horizontal asymptote? Yeah, and here it is. Fun stuff. Okay, so in this make-believe problem, we have ourselves what looks to be a table on a graphing calculator, and we answer a bunch of questions. Now let's take a good visual of what we have. All right, t is very small and it works its way up. H of t is very big and works its way down. So without knowing everything, this is basically the picture that we have. Okay, there's some curves probably somewhere built in there, but all I know is on the very left to the very right, we go up, down, and that pattern doesn't seem to stop. So find h of 999. Well, it's right there. Negative 478. Don't overthink it. Find the limit as t approaches infinity. As t gets larger, that number is getting smaller, 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 faster, so we can assume that number is just going to keep dropping down to negative infinity, like so. As t increases without bound, the h of t, now increases without bound is just fancy talk for the limit as t approaches infinity of h of t, which we already know what's going to happen. But what's going to happen as it increases without bound, the h of t, I don't know how it wants us to word this, but I stole this problem from the internet, so I'm just going to word it the way I want. We'll say decreases, because we already know it's negative infinity, so we'll just say it decreases and continue to use words. Find the y-intercept. The y-intercept exists where x is 0, or in this case t, and when t is 0, you're at 32. Find the limit as t approaches negative infinity. That means as we move to the left, my picture is moving up. The number is getting much, much, much larger as t gets much, much, much smaller, so we will say positive infinity. And as t decreases without bound, which is the same thing as what E is saying, the h of t increases, and that's the way we will word it. So we can say consistent with C. And there you go. Holy smokes, look at the picture on this one. We're answering like a few questions on this, so let's just jump right into it. We have ourselves a graph. It's probably a rational function because we have all these curves and explosions. We have asymptotes, we have leveling out, definitely a rational function. All right, so state the domain of f of x, use interval notation. The domain is basically where the x is being represented. Now we have two places where x is not represented. Anytime we see an explosion where it goes down and then reappears, there's an asymptote there. And it appears that one of my asymptotes is at -2, and the other asymptote appears to be at +2. So that means my domain is going to be everything but -2 and +2. How do I write that out? Well, in interval notation, we go left to right and we say negative infinity with parentheses, because we never include negative infinity, to -2, but don't include -2, so parentheses again, union. And then we pick up at -2 without including it. We go all the way over to regular 2, don't include it, union, and then regular 2 on forever. That's my domain. Find f of 9. That means when the x value is 9, what's my regular y value going to be? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like it's right there. So I'm going to go with 1. Find the y-intercept. That's where my line right here crosses the y-axis, and it happens right there, so we'll call you -2. Find the x-intercept. That's where my line crosses the x-axis, so right there at -1, and that's it. All right, so we've answered 4 of them. Let's clean this up a little bit, get a new color, and keep this train rolling. State the interval or intervals where f of x is increasing. All right, well, from the left to the right, decreasing, 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 disappears, way up here, decreasing, 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 disappears, way up here, decreasing, decreasing, decreasing. So where is it increasing? Never. State where the interval is decreasing. Well, it's always decreasing. We just figured that out. So it's basically the same as that. It's decreasing to -2, and then from -2 to 2, and then from 2 and on forever. So the same as a -infinity to -2 union, -2 to 2 union, 2 to infinity, and beyond. Well, not and beyond. There's no such thing. Find the limit, if you can read that. I can barely read it. As x approaches -infinity, that's what I'm hoping it says, of f of x. That means as you move to the left, where is my line going? Well, my line appears to be leveling off at the x-axis, which means it's never going to hit it, but it's approaching 0. And even if I couldn't read this, I mean, that's going to be the same thing, which I'm sure we'll get to. G says that we will, so I'm jumping the gun. As x decreases without bound, the f of x does what? Well, that's basically what I answered for k. K just says as x gets smaller, so as x decreases without bound is asking the same question. So what we'll do is we'll use words, and we'll say it approaches. That's not how you spell approaches. It approaches 0, or the x-axis. Find the horizontal asymptote. The horizontal asymptote, if not given a function, is where everything seems to level off. Well, on the left, it levels off at 0. On the right, it also levels off at 0. So the horizontal asymptote will be the x-axis. We write out the x-axis as y equals 0. Remember, a horizontal line is y equals a number, and in this case, it's going to be y equals 0. State the intervals where f of x is less than 0. In other words, where my line or my graph is underneath the x-axis. Well, it's underneath the x-axis all the time so far, and then it stops at -2. So right now, from -infinity to -2 is where it's underneath the x-axis. And then it reappears above the x-axis and hits the x-axis at -1. So we're not going to include -1 because we're not allowed to include 0. But after -1 and going on to regular 2 is where it's going to stay under the x-axis. Then it reappears above the x-axis and remains above the x-axis. So these are the only 2 intervals where it's less than 0. Switch colors again. Find the limit as x approaches regular infinity, if I can read that correctly. As we saw from before, it levels out right at 0, so that's going to be 0. As x increases without bound, the f of x, basically the same thing that L is asking from k, H is asking from G, it's going to approach 0. Look at me spelling it right. Estimate the points of inflection, which means where we have a change in concavity. Well, the only place I see a change in concavity is going to be like right around here, maybe? Maybe right around there. So we'll estimate 0, what was that, -2? We'll estimate it. You are going to remain concave down because you are never going to flip back down or anything like that. And you're going to remain concave up because you're never going to show back up again. So that's the only inflection point. Find the average rate of change over the interval -1 to 0. So that's -1. That's 0. The average rate of change is a slope where we go down 1, 2 over 1. So we'll say -2 over 1, which is -2. Holy Christmas, that's a problem. But we did it. Evaluate the limit as x approaches infinity of a polynomial over a polynomial. Now, whenever you're asked to find the limit as x approaches any of the infinities, this is what you're going to do. You're going to focus on the leading term divided by the leading term. Fortunately, I have the leading term on the bottom, and it's u. I don't have the leading term up on the top in the numerator yet, but this is how I can do it. Multiply the leading terms in each parentheses. That gets you 2x squared. Now your next step is going to be simplifying as much as possible. The x squareds both cancel out, and 2 over 4 becomes 1/2. Now that I have that, I can say the limit as x approaches infinity of 1/2. What I'm going to do now is plug infinity into x. Well, wait a minute. There is no x. So there's no infinity for me to plug in. So since I'm not plugging in anything, I'm just going to get 1/2. So the trick with this is if you figure out that the degree in the numerator is going to be the same as the degree in the denominator, your leading coefficients when simplified is going to get you your limit as x approaches either of the infinities. Again, if the degree in the numerator is the same as the degree in the denominator, look for your leading coefficients, simplify them, and that's your answer right there. Evaluate the limit as t approaches negative infinity of 2t cubed minus 3t over 5t squared minus 4t. Now, what you do whenever you're asked to evaluate a limit as it approaches either of the infinities is you locate the leading term in the numerator and the leading term in the denominator and focus only on those. Write those out like so and simplify as much as possible. All the t's on the denominator go away, and you're left with 1t in the numerator. So 2t over 5. Now that we have that, we can write this out as the limit of t approaches negative infinity of 2t over 5. As much as it sounds right not saying this, what you do next is plug in negative infinity into t. So that's going to be 2 times negative infinity over 5. 2 times negative infinity is negative infinity, believe it or not. Negative infinity divided by 5 is still a really large negative number, so it's still going to be negative infinity. And that's going to be my answer. So whenever you have a limit approaching either of the infinities and the numerator has a higher degree, expect to have some kind of variable left over in the numerator. You plug in the infinity that you're supposed to, and however the math works out is going to give you one of those infinities, whether it's positive or negative. Either way, if you're going to have a degree in the numerator higher than the degree in the denominator, and you're approaching one of the infinities, you're going to get one of the infinities for your answer. Evaluate the limit as x approaches negative infinity of 1 over x minus 4. Boom! Now, how did I do that? Well, if you have a higher degree in the denominator than the degree in the numerator, and x approaches either infinity, no matter what, you're going to approach 0. Why? Well, let's use common sense, okay? Let's use common sense. And again, this could be either infinity. All right, if I were to plug in like -1, all right, I'd get 1 over -1/5. Great. Okay. If I were to plug in -10, I'd get what? 1 over -1/14, much smaller number. If I were to plug in 100, I would get -1 over regular 104. So these numbers are getting smaller, and what they're doing is they're giving me numbers awfully close to 0. So as the denominator gets larger in either direction, your number is approaching 0. That's why. So no matter what, If you're finding the limit as x approaches either of the infinities and your denominator is a larger degree, no matter what, it's approaching 0, no matter what, end of story. All right, we have ourselves a nice little rational function, g of x, and we're being asked 6 questions about it. So first things first, the domain. The way you find the domain of a rational function is you figure out the numbers that make the denominator equal to 0. So in order to do this, what I have to do is I'm going to rewrite this guy. The numerator I really don't have to rewrite because the numerator isn't important for the domain, but I'm going to write it out anyway because I started it. And I had to factor out the denominator. X squared minus 9 is difference of squares. That factors out to x plus 3 and x minus 3. Now, the two numbers that make the denominator equal to 0 would be negative 3 and 3, which means I'm allowed to plug in any number I want except for negative 3 and positive 3. So that gives me a domain of everything, negative infinity, up to negative 3. I'm not allowed to plug in negative 3, so I'm going to union it and make it negative 3 again, because you're not allowed to include negative 3. Negative 3 to 3, union 3 to infinity. Okay? That's the domain. Now to find the y-intercept, I'm going to focus on when x is equal to 0. That's kind of a long way of doing it. So what I can do is I can FOIL out the top but only focus on certain things. Now I know what I can do. I know what's going to happen. All right. And I'm going to be a little lazy here. Since I'm answering questions about the limit, I'm going to kill two birds with one stone. I'm going to leave the denominator the way it was originally, and I'm going to find the leading coefficient and the last constant of what's completely up here in the numerator. So part number 1, the way you find the leading coefficient is you multiply the leading term in every factor. 4 times x is 4x squared. I don't care about what's in between. Don't care. The way you find the constant is you multiply every constant in every factor. So that's 4 times 5 times negative 2. 4 times 5 is 20. 20 times negative 2 is negative 40. So the y-intercept is going to be the constant divided by the constant. Negative 40 divided by negative 9 is just going to be 40 over 9. Now, the limit as x approaches negative infinity is found by dealing with only the leading coefficients. Now, my leading coefficient is 4x squared over regular x squared. So a little shortcut is I can view the leading terms, not coefficients, but the leading terms as 4 over invisible 1, or just 4. So when I plug in negative infinity in air quotes, when I plug in negative infinity, I get 4. And when I plug in regular infinity, I also get 4. Which means as x increases without bound, the g of x approaches 4. Remember, my end behavior gives me a y or a horizontal asymptote. And that horizontal asymptote is going to be at 4. As x increases without bound is just fancy talk for saying as x approaches infinity. So g of x is going to approach 4. Similarly, as x decreases without bound, the same exact thing is going to happen, and g of x approaches 4 once again. Okay? So 6 questions based off of this rational right here. Fun stuff. The function f is given by f of x equals negative x cubed, blah, 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 over 5x squared, blah, 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 which describes the end behavior of f. Now, why did I only mention negative x cubed and not everything else, and 5x squared and not everything else? Well, whenever you're trying to find the end behavior, you only care about the leading terms in the numerator and the denominator, so everything else is just coincidental. So I have negative x to the third, who cares about the rest, over 5x squared. What I do now is I simplify the x values as much as I can, and that gives me negative x over 5. Now, what you do to find the limit as x approaches negative infinity, and it's going to sound kind of weird, but the limit as x approaches negative infinity of this guy right here has me plugging in negative infinity for x. Negative infinity becomes positive infinity. Positive infinity divided by 5 is still positive infinity. So the limit as x approaches negative infinity is going to be positive infinity. So not you, and not you. Okay. Similarly over here, the limit as x approaches positive infinity is going to have me taking this guy and plugging in positive infinity. So negative positive infinity divided by 5 is going to be negative infinity, because negative infinity divided by 5 is negative infinity. So the limit as x approaches infinity of negative infinity is negative infinity. All right, so we have h of x. It's all, multiplied out and everything, and it's asking questions about domain, whole, zero, vertical asymptotes, horizontal asymptotes, y-intercepts. So what we need to do is we need to view this in its factored form along with its regular standard form. So the factored form is going to be, that is difference of squares, x plus 3, x minus 3. The denominator is two numbers that add up to negative 2, would multiply out to negative 3. So x minus 3, x plus 1. Now we see what's going to happen here. We see that we have an x minus 3 and an x minus 3. We'll deal with that when we have to, but not quite yet. The domain is any number that takes the denominator and makes it equal 0. Now the two denominators, and what I'm going to do is I'm going to look at each factor and I'm going to look at every number that makes it 0. My magic number for you is negative 3. My magic number for you is regular 3. My magic number for you is regular 3. My magic number for you is negative 1. Now, the domain is any number that makes the denominator equal to 0, and the numbers that do that are going to be 3 and negative 1. And if you're thinking, well, what about these? Aren't these going to cross out? Yeah, kind of, but the original problem looks like this now. And so we have to take into consideration the original problem before we cross anything out. So I'm not allowed to plug in negative 1, and I'm not allowed to plug in 3. So the domain is going to be everything up until negative 1, negative 1 to 3, union, and 3 on to infinity. That's my domain. My wholes are going to be any number whose factor is seen both in the numerator and in the denominator the same amount of times. X minus 3 appears in the denominator, x minus 3 appears in the numerator, which makes 3 a whole. So x equals 3 is a whole. My zeros are any number in the numerator that equals 0 that is not a whole. So 3 is not a whole because I'm not allowed to plug in 3 in the first place. I'm sorry, 3 is not a 0. 3 is a whole. 3 is not a 0 because I'm not allowed to plug in 3 in the first place. So 0 is negative 3, and that is it. My vertical asymptotes are any number that is seen in the denominator that is also not a whole. Negative 1 is the only vertical asymptote, and since negative 1 is a vertical asymptote, we write out x equals negative 1. The horizontal asymptote is where everything levels out. Okay, in other words, my end behavior. You find your end behavior by taking the leading term divided by the leading term and plugging in infinity. X squared over x squared equals 1. Plugging in infinity into 1 changes nothing. So my horizontal asymptote is the horizontal line y equals positive 1 because everything levels out at positive 1. My y-intercept is what happens when x is equal to 0. Well, when x is equal to 0, you go away, you go away, you go away, and you're left with just the constant divided by the constant. So negative 9 divided by negative 3 is positive 3. So there you have it. You're given a regular old rational function, domain, holes, zeros, vertical asymptotes, horizontal asymptotes, y-intercept. Hope this helps. Look at this graph of f. It's definitely some type of, rational function. We have ourselves what looks to be a slant asymptote. We have ourselves what looks to be a vertical asymptote, probably around 1, 2, 3, 4. So -4 is what I should have said. So dashed line through -4 if I knew how to draw a straight line. We should be able to answer some questions here. We got a hole right there. First and foremost, domain. The only number that you're not allowed to plug in appears to be -4 because that's where a vertical asymptote exists. So -infinity to -4, union -4 to infinity appears to be my domain. My hole seems to live right there, and that's at 1, 2, 3, 4, 5, 6, 7. So my hole exists at x equals 7. My 0 is any number that crosses the x-axis that's not a hole. Okay, I have two of them, one at -2 and one at +2. So my zeros exist at -2, +2. My vertical asymptote is that vertical line that cuts through -4. So that's the equation x equals -4. My horizontal asymptote is a straight line where everything levels out. Well, there is no straight line where everything levels out. It looks like we have a slant asymptote. And since we have a slant asymptote, we have no horizontal asymptote. My y-intercept is supposed to be an estimate, so I'm going to estimate that at, I don't know, a half, -1/2, I mean. So we'll say -1/2. We're estimating. We're not being perfect. That's for Jesus to do. But look at that. We answered a bunch of problems. Good job, everybody. All right, we have ourselves some weird-looking sine graph here, and we have a couple questions based off of it. So let's attempt to draw this out to the best of my ability. I am absolutely terrible at drawing these out, so I'll do the best I can. Magic happens at -3. Magic happens at 2, and then it's undefined at 0. It goes through 0 at -3. It goes through 0 at 2. It goes from positive to negative. So, I don't know, something like this. I'm so bad at drawing these. Something happens down here. Okay, and then it shows back up. It's undefined, which could mean one of two things, and then it reappears at its negative state, goes through 2, and remains positive all the way until infinity. Now, here's where we have to be careful. I have one of two options that could make something undefined. Option 1 means that this could be a vertical asymptote, or it could be a hole. The thing is, I don't know. But this is the picture that I have. Okay, this is the picture that I have. The graph of f has a maximum at -3 and a minimum at 2. No, that doesn't make sense. The graph of f has a minimum at -3 and a maximum at 2. No, that doesn't make sense. F has two distinct real zeros, exactly two of them, -3 and 2. Those appear to be the only zeros. So that checks out, but I'm always paranoid. I need to double check. F has exactly 3 distinct real zeros. No. The graph of f has a vertical asymptote at x equals 0. Again, here's the thing. That could be true, but I don't know because it could be a hole, and a hole is something that is undefined. So I can't prove that E is true. What I can prove is C is true because there's only 2 places where my line hits a 0, here and here. Because of the infinities, it's not going to come back down and hit a 0 anytime soon. C's got to be my answer because E can't be proven. Possible? Yes. Can it be proven? No. Let's go with C. All right, we have ourselves a rational function, and we are being asked to answer a bunch of questions about it. Now, let's take a look at what we have first. We see in the denominator multiplicity. This is what's called a perfect square trinomial, and we have multiplicity. When you're dealing with multiplicity and you're expecting things to be the same, that kind of changes domain, not so much domain, but whole, zeros, and vertical asymptote behavior. So let's do this first. Let's ignore the multiplicity part. We'll get to that in a second. Let's deal with the domain. The domain is what number am I not allowed to plug in? Any number or numbers that makes the denominator equal to 0, I'm not allowed to plug in. For example, 2 would make the bottom equal to 0. 2 is the only number that would make the bottom equal to 0, which means 2 is not allowed in my domain. So the way we write that out is we say negative infinity to 2, not include the 2, that's what the parentheses means, union, and then 2 on to infinity. Now I have to take into account this multiplicity thing. What I need to do is I need to factor the top part, the numerator. So I need to come up with two numbers that add up to 4 and multiply out to negative 12. And I think x plus 6 and x minus 2 should do it. Now I still have x minus 2 squared on the bottom. I'm going to write this out both ways. Not that it's necessary, but it might help me understand things a little bit better. X plus 6, x minus 2, x minus 2, x minus 2. Now, whenever you have multiplicity and you have repetition going on in the numerator and the denominator, this is what you're going to take into account. Okay, my magic number here is 2, my magic number here is 2, and my magic number here is negative 6. Whenever your multiplicity, and if you have repetition, whenever your multiplicity on the bottom in the denominator is an odd number more than whatever repeated factors you see up here, you are going to have a vertical asymptote. Okay, so basically the behavior of this happens. Now I know that's a whole, but this 2 is also the same exact number. So which is it? Is it a whole or is it a vertical asymptote? Well, since this goes away, the graph now behaves like this. Either way, you're not allowed to plug in 2. But now, since this part goes away, you are left with a vertical asymptote, and the whole behavior is now gone. So 2 is a vertical asymptote and not a whole. That leaves me with a negative 6 up here that I am allowed to plug in, and that negative 6 becomes a 0. So if you're wondering, all right, well then what's my whole? There is none. And again, that's because you have more factors on the bottom than you have up here that are the same thing. So that takes me to my limit notation and horizontal asymptote and end behavior and all that stuff, which is basically the same thing. Except for this part, limit notation of the vertical asymptote. Now, since the graph behaves like this, my picture is either going to look like this guy or like this guy, because now it behaves like this. And if I wonder, all right, well, which one is it going to look like? It's going to look like U, this one right here. And the reason why it looks like that right there is because both of my leading terms are positive. So it's going to take on this behavior. If I wanted to go into more detail, I can make myself a sign chart, but I'm not going to do that. So what it's asking me here is the limit notation of my vertical asymptote, which happens at 2, is going to look like this. As I approach 2 from the left side, that's what that little minus sign means, of what is it, h of x? I am going downward. So my limit as I approach 2 from the left has me going down here, which means negative infinity. Okay, let me scooch this out of the way because I don't need it anymore. My limit as I approach 2 from the right side, which means I'm coming this way, is going to be positive infinity. So h of x equals positive infinity. Horizontal asymptote is asking where this levels out. Well, in order for me to find out what my horizontal asymptote, where it levels out, I need to do the end behavior at the same exact time. So the way you do the horizontal asymptote, the end behavior, stuff like that, is you take a look at the leading term in the denominator and the numerator. So the leading term in the numerator is x squared. The leading term in the denominator isn't as obvious, but it's an easy fix. If I were to do x times x, or x times x, or x times x, I also get x squared. X squared over x squared simplifies out to regular 1. So my horizontal asymptote flattens out at regular 1, which is going to be the equation y equals 1. Which means my end behavior, as I move to the left, is going to flatten out at 1, and as I move to the right is also going to flatten out at 1. So the limit as x approaches negative infinity, as x decreases without bound, of h of x is going to be the same as the limit as x approaches positive infinity, and those both equal 1. Since I ran out of space there, I wrote it out as they all equal each other. But yeah, there you go. Kind of a complicated problem. Multiplicity never makes things fun, but we figured it out and we had a great time. Hope this helps. All right, section 1.9, poorly drawn, is asking us to find, in this case, the limit notation of a vertical asymptote. Now, we have two vertical asymptotes, one happening here and one happening here. Those are my vertical asymptotes. I'm going to try to draw the dashed line. I usually fail miserably. That's all right. And that's all right. So the way we write out the limit notation of my vertical asymptotes and what it means is we're looking at what's happening as the vertical asymptote, or as I approach the vertical asymptote from the left and from the right. So let's focus on this one at -2 first. If I want to describe or write out the limit as my x approaches -2 from the left, I'm going to put that little negative up there. That means from the left. I don't have a function, so I'm not going to call it f of x or anything like that. I'll just say equals. Now, what this looks like is I'm approaching my vertical asymptote. I'm approaching -2 from the left, and as I go towards -2, I shoot down here. And since I'm pointing downward, that means I'm shooting down towards negative infinity. Now, I'm going to do the same thing, but I'm going to approach -2 from the right side, so I put that little plus sign up here. As I'm going to -2 from the right side, I'm going to ignore all this stuff. I'm heading towards -2, and as I go towards -2 from the right, I'm shooting upward, which is positive infinity. That takes us to the limit as x approaches our next vertical asymptote, which is at 3. So the limit as x approaches regular 3 from the left has me traveling from the left, ignore this, traveling from the left, and as I go to 3, I shoot up, which goes towards regular infinity. The limit as x approaches +3 from the right side has me traveling from the right, and as I go towards +3, I also shoot upwards to positive infinity. Now, this happens because of even multiplicity. I don't know if we're going to run into that problem in a later problem, but yeah, that's why that happens when that happens. But that didn't happen here because I just gave you the pretty little graph. Thanks for watching. Hope this helps. Ooh, time to show off my ability to sketch a graph, which is bad. I'm given all of this information right here, so I'm just going to draw stuff on this picture and see what happens. At -4, I get 0. At -4, I get 0, so I'm going to put that there. Part A is done. At 6, I get 0, so I'm going to put a dot there. At 6, there I'm done. As I approach -3, from the left side, I hit negative infinity. Okay, so what that means is I have a vertical asymptote at -3. So let me try to draw the dashed line that represents the vertical asymptote. And as I go towards -3 from the left, I'm going down. So what's probably going to happen is I'm going to go up here, go through that purple dot, and come down here. But I'm not going to draw yet. I'll kind of wait until the end in case maybe it tells me where things level out or something like that. What else? At -3 coming from the right, I go to positive infinity, so that happens. Okay, so I'm going to have some type of vertical asymptote that as I travel from the left, I go down and then hits the vertical asymptote, reappears up here, and something else happens. So check, 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 check. At regular 4, from the left side, I hit infinity. So that means I have another asymptote. So at regular 4, I have an asymptote again. And from the left side, I'm going towards infinity. So that's going to happen. From the right side of regular 4, I go down to negative infinity, so that's going to happen. So probably what's going to happen here is I'm going to come somewhere up here, hit that purple dot, and go down there. But again, I'm not there yet. I'm too scared. As x approaches negative infinity, I go to 2. And as x approaches positive infinity, I go to 2. That's my horizontal asymptote. So I have a horizontal asymptote happening at 2. Oh yeah, also, by the way, forgot to tell you, I don't know why they waited for this at the very end. At 0, I hit 5, which means at 0, I hit 5 there. So now I have everything that I need. Okay, I have everything that I need. I know that in this chunk right here, I level out at regular 2, hit the purple dot, and then go down there at -3. So level out at 2, hit the purple dot, and then, oh gosh, I knew that was going to happen. Although that doesn't look half bad if I just scooch this over just a teensy. No, just a teensy. Let me try it again. Let me just try it again. Let me just try it again. Let me try it again. All right. I'm not going to edit this out. I'm going to keep it. The more time that I have on these videos, the more money I make. Boom. All right. Now I reappear up here, hit that dot, and then go back up there. So reappear up here, hit that dot, something like that happens. Then I reappear down here, go through that purple dot, and level out at 2. So down here, go through that purple dot, level out at 2. And that's my sketch. I'll give myself a pat on the back. That's not too bad. Not too good, but not too bad. But there you go, sketching a graph when given all this information. Hope this helps. Given the graph of f, which of the following describes the function of f? So it's given me all of this left-handed and right-handed notation stuff, and stuff either happens at -4 or just -4. So let's see what happens as the limit approaches -4 from the left side and the right side. Here's -4, okay? So the limit as x approaches -4 from the left of this function called f of x means I'm going to go all the way to the left. And from the left, I'm going to go to -4. And as I hit -4, I shoot up here, which means the limit as x approaches -4 from the left of f of x is going to be positive infinity because I go up here. Now the limit as x approaches -4 coming from the right means all this stuff that happens over here, who cares? But I'm going to pick up here. I'm coming from the right. I'm heading towards -4. And as I start approaching -4, I go down here, which means the limit as x approaches -4 from the right side of f of x is going to be negative infinity. So I need the one where from the left you go to positive infinity and from the right you go to negative infinity. So not you and you, right? From the left you go to positive infinity and from the right you go to negative infinity. So B is going to be my guy. And by the way, if you're wondering, well, what about something like E? Nah, don't worry about it. It's not real. It's not true either. Hope this helps. All right, I'm given a graph here and I'm being asked to find the limit notation of the holes. Now the hole exists where you have on your graph a little hole right there, which is a circle. Now the limit notation of a hole means as I move from the left and from the right towards that hole, where am I going? The hole exists when x equals 5. So coming from the left side, here in red, I would write this out as the limit as x approaches 5 from the left. That little negative on the top right means I'm moving from the left. When I move from the left, if I were to plug in 5, I would get something that doesn't exist, that's undefined. That's what a hole means. But as I approach 5 from the left, I seem to be heading towards that number 4 right there. So the limit as x approaches 5 from the left has me going towards the y value of 4. Now coming from the right side is a lot of the same. If I head towards 5, which is my hole, I would write that out as the limit as x approaches 5 from the right side, which means a little plus sign right there. As I approach the x value of 5 from the right side, I hit the same exact y value of 4. So the answer is going to be exactly the same from the left and from the right. And that's how you do limit notation of a hole. We are given a table of values here, and we know it's a rational function, and we're supposed to answer questions about limits as numbers approach -3 from the left and from the right, and then it rewords those. So we're given this table, and this table gives us values that kind of look like you would plug it into a TI-84 Plus and hit table, and something like this happens, but it's different. What it's telling us right here is -3 seems to be really important, and then we take something really close to it, and get even closer, get even closer, get even closer. Similarly, on the other side of -3, we take -2.9, which is really close to -3, and we get even closer and even closer and even closer. So what we want to do is we kind of want to draw ourselves like a fake graph centering around -3 and using the numbers -3.1 and -2.9, like that. Also, it looks like the magic number here is like 4.2-ish, and then something is undefined. We'll deal with that when we deal with that, but I'll put 4.2 here. Now let's focus on the left of this -3. At -3.1, I'm at 14.13. And then I get bigger, a little bit, but bigger, like $14.13 some cents, $14.15, $14.18-ish cents, $14.19-ish cents. What's happening is we start a little bit below 4.2, and this is 4.2, not -4.2. This is just me saying it's regular 4.2. See, look, fixed. So I'm starting out a little bit under 4.2, and then I hit undefined. Now, why would I hit undefined at -3? Because it's a vertical asymptote. So what's going to happen is I'm going to hover a little bit below 4.2, get bigger, 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 and then shoot up like that. Okay, that's what happens at asymptotes. Similarly, over here on the other side, at -2.9, I'm at 4.37, which is somewhere above 4.2, and then I get smaller, smaller, smaller. Okay, but what's most important is I hit undefined again. So moving from the right to the left, my values get smaller. So at 2.9, I'm at like 4.3. And as I get closer, I'm at like 4.30 and then 4.2-ish. So what's going to happen is this is going to happen. Okay. So now based off of this picture, we can answer some of these questions. The limit as x approaches -3 from the left means I'm traveling from the left and I'm moving up as I go towards -3, so my answer is going to be positive infinity. My limit as t approaches -3, positive means from the right, so I'm coming from the right, I'm approaching -3, and then I shoot downward, which means it's negative infinity. So as t approaches -3 from the left, the d of t goes towards infinity. So we'll use a word like increases so we don't repeat ourselves. Increases. And as t approaches -3 from the right, which is what this is saying, the d of t decreases because it's going towards negative infinity. So kind of a very bizarre problem, but nothing is impossible. Hope this helps. Look at this wonderful graph. Look at this graph. Isn't it neat? It's asking you a lot of questions about this graph. I see here we have a hole. I see we have an asymptote. So let's just get right into it. F of 6. F of 6 means if I were to plug in 6, what value would I get? It looks like if I plug in 6, it kind of hits my graph here at around 6. So I'll say it's 6. I don't know, maybe it's 5. If you have better eyes, you can answer it better. But f of 6 means plug in 6, and what do you get? Well, if I plug in 6, it looks like I get 6, maybe 5, but I'm going to say 6. I already wrote it down. Let's plug in 2. Oh, no, I can't, because this is a vertical asymptote. So me plugging in 2 is impossible. So we'll say that that is undefined or undefined. The limit as x approaches negative infinity. Ooh, what does that mean? That little negative means from the left. So here I am coming from the left. I'm approaching negative 5, and here I am. Oh, but that's a hole there. So at negative 5, I don't have any actual value. But as I go towards it from the left, I am approaching this value, which appears to line up perfectly with 2. So the limit as x approaches negative 5 from the left lines up with 2. Remember, limit is not an exact answer if you're approaching something. It just means that we're basically at 2, so let's just call it 2. This is very similar. We're approaching negative 5 from the right side now. So when we do that, negative 5 from the right, we're hitting the same exact value because it's a hole. So the limit as x approaches negative 5 from the right is also 2. Okay, switch colors, because now we're going to focus on approaching 2 from the left. So here I am from the left, I'm approaching 2, and as I approach 2, I'll never hit it, and instead I'll just go down here. What's down there? Negative infinity. The limit as I approach x or at limit as x approaches 2 from the right side, a little positive, means here I am coming from the right, I'm heading to 2, I'm never going to hit 2, but I'm going to go way up here, which means regular infinity. Okay, so usually when you approach a hole, you're going to get the same thing from the left and from the right, but when you approach an asymptote, it all depends on where your asymptote splits up, or where it makes your graph split up, I should say a little bit better. The limit as x approaches negative infinity, which means I'm basically moving to the left. So as I move to the left forever and ever and ever, where is my graph going? That way, which is up, which is positive infinity. As x approaches positive infinity, that means I'm moving to the right. My x values are increasing without bound. And as my x values are increasing, my y values, or f of x values, I should say, are also increasing, which means that side is also going to infinity. How about that? Catch me outside, how about that? Now my domain is what numbers am I not allowed to plug in? Let's name those and make sure I don't include those in the domain. I'm not allowed to plug in negative 7 because I have a hole there. I'm sorry, that's a negative 5, not negative 7. And I'm not allowed to plug in regular 2 because I have an asymptote there, a vertical asymptote. So every value seems to be included except negative 5 and 2. So how do I write that out? Well, everything from negative infinity to negative 5, but not including negative 5, union. Everything from negative 5, but not including it, to 2, but not including it, union, and everything to 2 on forever. So there you go. Pretty intense problem. It's like if we're going camping. Intense. Ha ha ha. Like and subscribe. Function f is given by f of x equals x squared minus 9 over x squared plus 8x plus 15. Which of the following describes the function f? They care about holes. Holes exist when you have a parentheses and you have the exact same amount of parentheses up here that you have down there when these two guys are exactly the same. So what I need to do is I need to factor the numerator and I need to factor the denominator and see if I have something up here that's exactly the same as something down there. If I do, hole. Now I have x squared minus 9, that's a difference of squares, so two numbers that multiply out to negative 9 that are the same digit are going to be x plus 3 and x minus 3. Two numbers that add up to 8 and multiply out to 15 are going to be x positive 3 and x positive 5. Now what I care about are the numbers that make each factor equal to 0. Negative 3 would make u equal to 0. Regular 3 would make u equal to 0. Negative 3 would make u equal to 0. Negative 5 would make u equal to 0. I only care about one thing here, and that is the whole. Again, the whole exists when I have a parentheses up here that's the exact same as the parentheses down here, and no more repeats anywhere else. That happens right here. So my factor is x plus 3, but the magic number where that happens at is at x equals negative 3. So there is a whole at x equals negative 3. And that's my guy, baby. Divide this guy using long division and synthetic division. All right, so whenever you're being asked to do long division or synthetic division with polynomials, you need to make sure things are in descending order or standard form and that you're not missing anything in between. X squared, regular x, and 4. Good, perfect. X and regular number, good, perfect. So I'm not missing anything in between. Let's do long division over here. Okay, the way you set up long division is you put the denominator on the left, you put the numerator right here, and then your quotient is going to be what you get up here. So let me write this out. Now, the first step is basically like regular old long division. You take your factor and you multiply, or you say to yourself, x times what gets me x squared? Well, x times x gets me x squared, so I'm going to put x right there. Just like regular long division, you take that x and multiply it to your factor. X times x plus 6 is going to be x squared. X times 6 is going to be plus 6x. You take this green line and you subtract the entire line, which means you flip the signs of both of these. So this will always disappear. And now I have negative 9x minus 6x, which is negative 15x. Drop down the plus 4 and repeat the process. Okay, negative x, or regular x rather, times what gets me negative 15x. X times negative 15 gets me negative 15x. Take that negative 15 and multiply it to everything here. Negative 15 times x is negative 15x. Negative 15 times 6 is negative 90. Subtract this entire row, which means you flip the signs of everything, and this gives me a remainder of 94. Now, I will write out now that this is a remainder of 94, and in a minute I'll explain what that means, but we're not there quite yet. Let's do synthetic division. A lot of people prefer synthetic division because it's faster. So synthetic division is going to look a little something like this. You make a little box up here, you make a little box down here. In this box, you put the number that makes your denominator equal to 0. The denominator equal to 0 would have negative 6 make that happen. So I'm going to put negative 6 in here. Up here, I'm going to put the coefficients of everything up here in the numerator. So invisible 1, negative 9, and 4. So that's your synthetic division setup. Step number 1 with synthetic division is you drop down the first term. Take that number and multiply it to your root here. 1 times negative 6 is negative 6 and write it there. Add these two and get negative 15. Repeat, negative 15 times negative 6 is 90. Add these two and you get 94. Now what's that 94? That's your remainder, just like we had over here. Now the way you answer these problems to its completion, if you're being asked to just do division and nothing else about like slant asymptotes, that'll be my next video. What you do is you say, all right, my answer is x minus 15. However, if you have a remainder, the way you write out your remainder is you say plus that number, 94, over your factor x plus 6. And that'll be my answer to this guy. Okay, and what that looks like here is you put 94 over x plus 6, you leave negative 15 on its own, you attach x to 1. But there you have it, long division, synthetic division, tons and tons and tons of fun. Write the equation for the slant asymptote for the following function. In order for you to know that you have a slant asymptote, one thing needs to happen. the degree in the numerator has to be 1 higher than the degree in the denominator. Does that happen here? Yes, it does. Now, the way we set this up is we do polynomial long division. It's important for you to understand that if we're going to do polynomial long division, everything has to be in order, and anything in between or at the end that's missing has to be filled in with zeros. What do I mean? Well, the numerator is always the guy that goes into the division symbol. So I'm going to go 9x to the 4th. I'm missing an x cubed here. So I have to replace that with 0x cubed. And then I keep going in order. Minus 5x squared plus 3x minus 6. Make sure it's in descending order, and if it's not, change it that way. Now, this guy is going to be the factor that's being divided from it, so I'm going to write that over here. And even though it might not be necessary, I always like to add those extra things at the end that aren't there. Like I'm missing an x and I'm missing a regular value, so I'll add 0x and I'll add 0. Is it necessary? I don't know, but I do it anyway. This is how you do polynomial long division. 3x cubed times what gets me 9x to the 4th? Well, 3 times 3 is 9, and x cubed times x is x to the 4th. Take that number and multiply it to the entire factor. 3 times 3x squared is cubed is 9x to the 4th. This will always be the same unless you did something wrong. 3 times x, or 3x times negative 4x squared is going to be negative 12x cubed plus 0x, because 3 times 0, plus 0x. That should be squared. My bad. Now you subtract this entire row, which means you flip the signs of everything in here. This will disappear. This will become regular 12x to the 3rd. Drop down the minus 5x squared. Drop down the 3x. Now this last part, oh, and always drop down the negative 6, even though it's not that important. Now, why did I just whisper that? How dare I say it's not that important? Because my next step is to repeat what I did at the very beginning. 3x cubed times what gets me 12x cubed? Well, 3 times 4 is 12. And x cubed times 1 is x cubed, so I don't need anything more. Now, at this stage, I'm done. And if you might be thinking, well, you have to multiply 4 to that and find your remainder. No, I don't. I don't care about the remainder when it comes to my slant asymptote. Once I get a linear equation in slope-intercept form, I have my slant asymptote, and the equation for my slant asymptote is 3x plus 4, y equals 3x plus 4, and that is a line in slope-intercept form. So that's it. I'm done. Given the table of values for f, blah, 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 let g of x equals f of x plus 2, and then find g of 2. All right, so if g of x equals stuff, then g of 2 means replace every x with 2. So f of 2 plus 2. What's f of 2? Oh yeah, up here. When x is 2, f of 2 is 10. So f of 2 is 10. So let me replace f of 2 with 10. And 10 plus 2, let me get out my calculator, is 12. So g of 2 is 12. F of x equals 2x squared minus 3x plus 1. F of x minus 2 plus 5 happens to be g of x. Find g of x. So in order for me to find g of x, what I have to do is I have to take f of x, which is this guy right here, and replace every x with x minus 2. So f of x minus 2 means I write out f of x, but replace every x with x minus 2. So 2 times x minus 2 squared minus 3 times x minus 2 plus 1. And then at the very end here, we still have plus 5. So g of x is f of x minus 2 plus 5. This is a perfect square trinomial, so you become x squared minus 4x plus 4. U can be distributed, so negative 3x plus 6. You guys can combine to make 6. U can be distributed, so that can be 2x squared minus 8x plus 8 minus 3x drops down. These guys can combine to make 12. And then U are alone, 2x squared. Negative 8x and negative 3x make negative 11x. And 8 plus 12 makes 20. So that's what g of x is. Isn't that nice? Sure is. It sure is nice. Answered it for you. All right, look at this graph. We are asked to find g of x if g of x is negative f of x plus 3 plus 2. All right, this is going to really put my ability to draw to the test, so wish me luck. It's not going to be pretty. First things first, you have a negative in front of f of x. The first thing that you're going to do is you're going to reflect this guy right here over the x-axis. This is called a vertical reflection. So I'm going to try to do this in one picture. Wish me luck. Okay, so far so good. And then it kind of goes like that. And then it kind of goes like that. So I will give myself a little bit of credit. That's not too bad. Now, what we have inside this f of x is plus 3. Plus 3 inside the f of x means we move to the left 3 times, also known as a horizontal translation of negative 3. The reason why I wanted to draw this so accurately in one step is so I could do that here. Move over 1, move over 2, move over 3. 3. There we go. Okay? Still looks pretty decent. I'll probably have to outline it when I'm done, but that's all right. The last thing that I see is this plus 2 hanging out at the end here. Plus 2 means you're going to go up 2. That is called a vertical translation of positive 2. So let me show that. Up 1, up 2, and that right there is what my final picture should look like. Now let me outline it a little bit. Outline it again, make it look prettier. This is supposed to be like a nice little concave up-looking thing. And then it's a straight, sharp line here and a straight, sharp line there. Great. Graph the g of x done. State the domain of g of x. Well, g of x is going to be everything from negative 8 all the way to 0 and including. So we'll say negative 8 to 0 and including. State the range of g of x. It goes as low as negative 2 and peaks out at 1 and including. So we'll go from negative 2 to positive 1. Find g of negative 2. That means go to negative 2 and see where my g of negative 2 lives, and that appears to line up with a regular 1. Find the zeros of g of x. Well, the zeros of g of x seem to be right here, and right here. So that's where my graph, my new graph, crosses the x-axis. So that would be at negative 8, negative 4, and 0. And find the y-intercept of g of x. Just so happens that the y-intercept of g of x is right there, exactly where it was at the origin. So we will say that the y-intercept is the point 0, 0. I hate these problems because I have to draw things and I'm not good at drawing, but you know what? It's okay. Ended up all right. Thanks for watching. The function f and g are defined for all real numbers such that g of x is negative f of x plus 5. Which of the following sequences of transformations maps the graph of f to the graph of g in the same xy plane? I'm looking at this right here. And there's two things that I see. First thing that I see is a negative attached to f of x. Whenever you have a negative attached to f of x, you see what's called a vertical reflection over the x-axis. So that's step number 1, a vertical reflection over the x-axis. So whatever picture we have, after we reflect it, we move up 5. Okay, now moving up 5 is just fancy talk, or not fancy talk, for a vertical translation of positive 5. So a vertical translation of positive 5. Which of these gives me a vertical reflection x-axis and a vertical translation of 5? No. Vertical reflection of f by 5 units. Well, that does happen, but that happens second. Vertical reflection of the graph of f, yes. Followed by a horizontal translation? No. A vertical reflection of the graph of f, followed by a vertical translation of the graph by 5 units. The answer is D. Given the graph for f has a domain of -4, 3 and a range of 3, 9, but not including, let g of x equal negative f of x plus 5 plus 2. Find the domain and range of g of x. So I need a visual of what's going on here. I see 3 things going on. Always deal with the fact that there's a negative in front of f of x. That tells me I have a vertical reflection over the x-axis. So I will say step number 1, what we're going to do is we're going to reflect over the x-axis. Okay, vertical reflection. Now what I'm doing is I'm adding inside the f of x part. That means I have a horizontal translation of -5. Remember, whatever you're doing inside the f of x, you do the opposite. So a vertical, or a horizontal rather, translation of -5, so I'll write out ht of -5 is the same as me moving left 5. Okay, but I'm going to keep that ht of -5 there. You'll see why in a minute. After that, we add 2. That just means you move up 2, also known as a vertical translation of +2, which means you move up 2. All right, so I'm dealing with a picture where I have 2 things. All right, I have some kind of picture graph that goes from -4 to 3 and 3 to 9. So, something like this happens. Okay. Something like that happens. The first thing that I do, and let me kind of write out the steps for my domain right here and my range right here. The first thing that we're going to do is we're going to flip this over the x-axis, which means this now shows up down here, but more upside down. Now, how did that affect my domain? It didn't. So my domain, as of now, stays exactly the same. So my domain is still -4, 3. How did that affect my range? Well, if I flipped it upside down, then 3 becomes -3 and 9 becomes -9. So now my range is -9 to -3. Okay, I'm not going to write out -3 to -9, although the temptation is there. It's just backwards if I do that. Now what I do is I move 5 spaces to the left. 1, 2, 3, 4, 5. Now, how does that affect my range? It doesn't. So right now at this very moment, my range stays the same. How does that affect my domain? Well, if I move left 5, that means I subtract 5 from the x values of my domain. -4 went to -9. And regular 3, which was over here, went to -2. So maybe this picture should be a little bit more over here. Something like that. Okay? So 3 becomes -2. Now I'm going to move up 2. Boop, boop. Again, the picture is probably not accurate, so in fact, if I put it there, it'll be a little bit more accurate. So what does that look like for my domain? Nothing. Nothing changes for my domain, as I called it. But my range goes up 2, which means I'm going to add 2 to each value in my range. So that becomes -7, and that becomes -1. So there you have it. These problems are absolutely awful. This is the way that I viewed it. This is the way that I did it. Is it the best way? I don't know, but is it the way that makes sense in my pea brain? Yes. Thanks for watching. Given f of x equals x squared minus 3x plus 2, let g of x equals 2 times f of x plus 4. Find g of x. All right, so basically g of x says take f of x, don't change it, but multiply 2 to everything, and then add 4 when you're done. So g of x is going to be take f of x multiply 2 to it, and then add 4 when you're done. So basically, it's just, like simplify distributive property here, combine like terms. This becomes 2x squared minus 6x plus 4, and then plus 4 drops down. And then simplifying this one step further is going to be g of x equals 2x squared. Nothing combines with u. Nothing combines with u, but you make plus 8. Kate plus 8, or John and Kate plus 8. Remember them? John Goslin, Kate somebody. Thanks for watching. Given the table of values for f, let g of x equals 5 times f of x minus 1. Find g of negative 1. All right, I have a table of values, and f of x can be found from this table. I'm not trying to find f of x, though. I'm trying to find g of negative 1. Well, what's g of negative 1? G of negative 1 is 5 times, f of negative 1 minus 1. F of negative 1 means let's go up to this table, and when x is negative 1, I get 12. So f of negative 1 is just, 12. You become 60. You become 59. And so g of negative 1 is 59. Easy peasy lemon squeezy. The function g is defined by f such that g of x equals 3 times f of 2x minus b. If f of 2 is a, f of 4 is 8, g of 1 is 7, and g of 2 is 19, what is the value of a? Holy crap. Well, let's see what I can do. Okay, let's see what I can do. I'm given g of x equals stuff, and I'm told that f of 2 equals stuff, and f of 4 equals stuff, and g of whatever. Let's find the things that I can find. Let's find out what g of 1 is. Okay, g of x is that guy right there. So g of 1 is going to be 3 times f of 2, replace x with 1, minus b. So this simplifies to 3 times f of 2 minus b. Ooh, f of 2 is a. So this becomes 3a minus b. Now, does that get me anywhere? No, it's asking for the value of a, and, I have to do a little bit more because there's no b here, so I'm not quite done yet. So I found g of 1. Let's find g of 2. G of 2 is going to be 3 times f of 2 times replace x with 2 minus b. That becomes 3 times f of 4 minus b. Oh, look, f of 4 is 8. So 3 times 8 minus b is going to be 3 times 8, which is 24, minus b. Now, this is what else we know, because right now I'm not really getting anywhere, but here's what else I know. I know that g of 2 is also 19. I also know that g of 1 is 7. So what I can do is I could solve both of these equations and see what I come up with. Well, first off, let me do this, because now what I have is I have a system of equations where I have 7 equals 3a minus b, and I have 19 equals 24 minus b. I can find b right here in this equation right here. So if I take this bottom equation and subtract 24 from it, I get negative 5 equals negative b. If negative 5 is negative b, then positive 5 is positive b, so b becomes 5. I could take that guy right there and the top equation and replace b with 5. 7 equals 3a minus 5 has me adding 5 to both sides to get 12 equals 3a. Divide both sides by 3, and after all of that, a is 4. So a pretty gross problem, not a fun problem at all. Again, I stole this from the internet, so I don't know. It is what it is. Hopefully you never see a problem like it, but we did it anyway just in case. Select the appropriate model for the data. Is it linear? Is it quadratic? Is it cubic? This is what you're looking for. In order to find out from a table if something is linear, quadratic, or cubic, you need to find the rate of change as long as these guys go up by the same number. That's called equal length input value intervals. So if something's going to be linear, that means to get from 4 to 15 and from 15 to 50 and from 15 to 121, these have to be the same number. Well, to get from 4 to 15, you add 11. To get from 50 to 50, you add 35, which means right off the bat, it's not linear. This one has you adding 71. This one has you adding 119. And this one has you adding 179. So is it linear? Nar. Nar, as my friends from down under would say. Let's try it again. If it's quadratic, then the rate of change of the rates of change are going to be the same. So how do we get from 11 to 35? Add 24, of course. And from 35 to 71, add 36, of course. So it's not going to be quadratic because these numbers are different. So you add 48, you add 60. So it's not quadratic. So in order for something to be cubic, the rate of change of the rate of change of the rate of change has to be the same over equal length input value intervals. So how do I get from 24 to 36? Add 12. How do I get from 36 to 48? Add 12. How do I get from 48 to 60? Add 12. Is it cubic? Yep. So this is cubic because the rate of change of the rate of change of the rate of change are the same over equal length input value intervals. Isn't that fun? A patient receives a dose of painkiller. The function p of t equals, in the numerator, 2t squared plus 10t, denominator t cubed plus 1, and it models the amount of painkiller in the bloodstream over time. T is hours. P is painkiller in milligrams. It's a calculator problem. It's a calculator problem. We're going to need it with this ugliness. So part 1 is going to be find P of 2. Part 2 is going to be finding the average rate of change. And part 3, also known as C, is going to be the maximum amount of painkiller. So let's whip out a calculator, do each part at a time, see what we end up with. All right, so first things first, we have to plug in this formula. Whenever you're plugging in a formula, two things in this case, t's or x's, that's fine. But thing number 2, since we have a fraction, let's make sure we wrap the entire numerator in parentheses so that we have 2x squared plus 10x all in one parentheses. Then we can divide t cubed, so x, we'll do math 3 for cubes faster, plus 1. All right, hitting graph, there you have it. Now what we're going to do is part number 1 is asking us to find P of 2 and explain your solution in context. Two ways that we could do this. The easiest way to find P of 2 is by hitting second table and going down to 2, that's our P of 2, which is 3.11111. So let's go back to our slides and write out 3.11111. All right, so we ended up with 3.111 going on forever. And what that means in context means after 2 hours, we had 3.111 milligrams of painkiller in our bloodstream. So 3.111 milligrams of painkiller in the bloodstream at 2 hours. And so we'll write it out that way because we don't have space to write everything else. B is asking us to find the average rate of change from t equals 1 to t equals 2. Let's write out B here because I, again, stole this stuff from the internet and I didn't give myself a whole lot of space. The average rate of change formula is f of B minus f of A over B minus A. So in this case, what we're going to do is we're going to find out what f of B is, which we already did. If it's 1 to 2, that would be like an A and that would be like a B. So we know what f of B is. We know what f of 2 is. Minus f of 1, we don't know what that is. All over 2 minus 1. So let's run to our calculator and figure that out. Part 2 of this is asking us to find the average rate of change between the intervals 1 and 2. So I'm going to go back to my table. Second graph goes back to my table. I'm going to use the values for P of 2, which I already found out to be 3.11111, and P of 1, which was 6. So I'm going to use 6 and 3.11111 in that order. So while I'm here, I might as well do it because the numbers are friendly enough. Parentheses 3.111 minus 6 all over 2 minus 1. So divided by 2 minus 1, I think I can handle the 2 minus 1 part, but I'm typing it out anyway because it takes time. And we get negative 2.889. So let's go back to our slides and figure out what that means in the real world. All right, so the calculator reminded us that that was 3.111 minus our new value, which was 6, all over 2 minus 1, which ended up being 1. Typing that out in our calculator was negative 2.889. Now, what that means is at this moment between hours 1 and 2, we lost 2.889, lost because it's negative, milligrams of painkiller. So that's the value that we get. And again, that means in the real world that we went from 6 to 3.111 milligrams of painkiller in our bloodstream. And so, you know, that's the rate per the 1 hour that we had. Now, C is asking us to find the maximum amount of painkiller. And so we're going to use our calculator to use the maximum value and find out what we get. Our last thing we have to do is find the maximum amount of painkiller. So let's go back to our graph. And we have this picture where when time equals 0, and by the way, we don't care about negative time because that doesn't exist in the real world. It shoots up and then it comes back down. All right, so our max lives right around here somewhere. The way we can calculate our maximum is we go to second calc and use the maximum value 4. So obviously it comes up and it goes back down and it never, reappears. So I'll use 0 as a left bound. I'll use, I don't care, 6 as a right bound, enter. And so it's going to tell me my maximum is going to live between 0 and 6, which looks to be the case. So hitting enter one more time tells us that a maximum occurs at 8.51 hours. And that maximum is going to be 6.161, I think, was milligrams. So let's go back to our slides and write all that stuff out. So part C, the maximum value ended up being 6.161 milligrams, and that happened at 0.851 hours. So calculator problem, lots of fun. I hope you'd enjoyed it as much as I did. A rectangle is inscribed a circle with a diameter of 12. Here's my rectangle living inside, touching the outside of the circle. Diameter right there is 12. It gives us a width of x, tells us the other width is the square root of 144 minus x squared. They get that from the Pythagorean theorem just for fun. The function a of x is that guy, x times the square root of 144 minus x squared. So again, that comes from, that times that area formula, and that models the area of the rectangle. Great. What is the restricted domain of the function? This is asking us what values am I allowed to plug in? Well, first things first, we're looking at this rectangle right here, and this rectangle is going to tell us what we're allowed to plug in. Now, if we're going to represent x as a side, you are absolutely not allowed to plug in any negatives because you can't have a negative side, so negatives don't count. I also can't have a side that is 0. But I could have a side that's 0.1. It would be a very skinny rectangle, but I could have a side that is 0.1. So basically, as long as it's greater than 0, I'm allowed to plug it in. Now, what's the largest value I'm going to plug in? Well, as we see this square root right here, that tells us right there that if I have 144 minus something, that at some point there's a possibility that I end up with a negative square root, and you can't have negative square roots. So what number would make this square root equal to 0? 12. Because 12 squared is 144, and 144 minus 144 is 0. So does that mean 12, put a little bracket there, is going to be the absolute largest number that I can plug in? No. I'm not allowed to plug in 12. I'm allowed to plug in 11.99999, but if I plug in 12, then all of a sudden I'm saying I have a right triangle with a hypotenuse of 12 and a leg of 12, and geometry says that's against the law. So my restricted domain is everything from 0 to 12, not including 0, not including 12. Yippee. Part 2 is asking us what's the restricted range of the function. In other words, what is the largest and smallest possible values that I can get when I plug in 0 or something close to 0 and 12 or something close to 12. So I'm going to run to my calculator. I'm going to plug numbers in that are awfully close to 0 and plug numbers in that are awfully close to 12 and see what I end up getting. All right, so let's go to our calculator and type out this function. We've got x times the square root of 144 minus x squared. Now, what we know is our domain is everything from 1 to 12. So from 0 to 12, not including. So let's actually change our window and make it like -1 to 13 so we can see what we need to see. Okay? Boom, graph. Now it shoots way up here, so maybe let's maximize the window to, I don't know, 100 and see if that seems to be good enough. Hit graph again, and that does seem to be good enough. Oh, how nice. Now notice how it cuts off at 12. That's because we already know we're not allowed to plug in 12 or anything after that. Now, why doesn't it cut off there? Well, because our calculator doesn't realize we're doing a real life problem. So, it doesn't realize we're doing like negative x stuff. Okay? Now, what I need to do is I need to find my range. Without plugging or typing anything in, I know that my range is going to be from 0, but not including 0, to 199. So my smallest value, I already know what's going to happen. It's going to go through 0. My smallest value is 0.000001. So my smallest range, if I have like the skinniest triangle, is going to be 0, just not including 0. So I'll make sure I write that down. Now, in order to find what my maximum range is, I have to go find my maximum. So I'm going to do second calc. I'm going to set a range for the maximum, and it looks like it's going to happen between, basically, I'm at 6, so I might as well hit enter for that. And as long as I go to the right of the bump there, hit enter on that, my maximum is going to live somewhere in between. And my maximum happens when x equals 8.4, blah, 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 blah. But that maximum value is 72. So my range is going to be between 0 and 72. So let's go back and write that out. All right, so what I got was basically 0.000001. So I'll say 0, but not exactly 0. And pretty much 72, but not 72. It's got to be smaller than 72. So my smallest area is going to be like 0.00000, and my largest possible area is going to be like, 79.99 or 71.9999999. What is the maximum area of the rectangle? Well, let's go back to our calculator, type that in, and see what the maximum area is. Hey, what's the maximum value? 72, stupid. Go back. Well, I didn't really need to do that because I did that in part B. So 72. I don't know why I did that. Dummy me. But, anyway, thanks for watching. The data shows the salary in thousands of dollars for employees given their year's experience. So we have this information right here, and it looks like it's a calculator problem. So what we're going to do is let's throw all of this stuff into a calculator. All right, after we're done throwing it into a calculator, we'll answer these three questions. And it's asking us to use regression. So rather than doing the whole, like, let's see if this adds up and do that thing, let's let our calculator do the job, because I have a feeling it's not going to be absolutely perfect. So let's just plug it in to our calculator and see what our calculator gives us. All right, so let's type some of these numbers in. Stat, edit. Now, I think what I said before is, rather than like counting, if you're already noticing already, I really can't do the, hey, let's count and see how far apart these guys are, because these numbers are not equal length input value intervals. So forget what I said back there like 30 seconds ago. 2, 4, 5, 8, 9, 12, 15. Then we got 48, 54, 58, 68, 73, 80, 88. All right, no mistakes at all. First thing that I have to do is figure out if this is linear, quadratic, or cubic. So why don't I graph these points on the graph? Now, hitting graph won't do anything for me. What I have to do is I have to hit second, stat plot. I have to turn the stat plot on. And already what it's going to do is it's going to give me the dots according to the stuff that I plugged in. Before I hit graph, since I'm using stat, I need to go to zoom first and do zoom stat. So go to 9 and we'll see our dots. Now those dots aren't in perfect order, but you know what? They look pretty linear to me. So we're going to go with linear for that one and write that down. All right, so basically the dots were in a nice straight line, not perfect, but good enough. So I'm going to circle linear for that one. Now that I know that it's linear, when it asks me to write an equation of the regression curve, I'm going to use linreg and see what equation I get in my calculator. Now part B is asking us to find the equation of the regression curve. We know that this is linear. So let's quit out of this. Our points are still in the thing. Let's go to stat, calc, and use linreg. Use 4. So when I go to 4, and since, by the way, C is asking me to use this equation to plug in 11, what I'm going to do is when I go to store regression equation, I'm going to hit vars, y vars, function, y sub 1. And what this will do is this will store whatever equation that I get into y equals, so I can do part C without having to type out the whole world. So if I hit enter, it gives me my equation. And so when I round it to 3 decimal places, it's going to be y equals 3.137x plus 42.349 end. Mr. Calculator says that the equation is y equals 3.137x plus 42.349. That's my equation. Use that equation to predict the salary of an employee with 11 years experience. So I'm going to throw that back into my calculator and see what I get. Now, since we stored that equation into y equals, if I want to find out what happens at 11, all I have to do is hit second table, go down to 11, and see what number I get. And that number I get appears to be 76.8603, blah, 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 blah. So when I write that out, I have to remember this is in thousands, so I'll make sure I account for that. But that's how I do this problem on my calculator. Easy peasy. Now at 11, my calculator gave me something like 76 point blah, 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 blah. But this has to do with 76,000 blah, 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 blah. So the number in my calculator was 76.86036,036. That translates to $76,000. $860.36. Baby, that is a nice bit of coin. A linear regression model is used to construct a function model P that models the price over the given years. If T equals 1 corresponds to 2012, T equals 4 corresponds to 2015, and this pattern continues, which of the following defines the function P? So I'm awful at these, so I have to write this out. 2012 is 1, which makes 2015 4, which makes 2018 7, which makes 2019 8, which makes 2020 9, which makes 2022 11. Never forget. All right, so let's throw that in our calculator and see what happens. Stat, edit. Let's type in those awful numbers. The numbers that we wrote before were 1, 4, 7, 8, 9, 11. Never forget. Then we end up with the other numbers, which were 7.96. Was it 96? Yep. 8.17, 8.97, 911 again, never forget, 916, and 1012. 1012. This problem is asking us to find linear regression. So let's go to stat. Let's go to calc. Let's hit 4. I don't need this equation again, so I'll just hit enter, not need to store it. And I end up with 0.206x plus 7.540 or 7.541, which appears to be A according to our problem. Okay, it's A. Thanks for watching. Bye. A membership to World Fitness costs $75 per month and includes 10 free fitness classes. Any fitness classes attended after the first 10 free fitness classes costs $5 each. So basically, it costs $75, and once you hit 11 classes, it's $80, and then 12 classes is, you get the idea. Function C is used to model the cost of a monthly membership to World Fitness, where N is the number of fitness classes taken and C of N is the cost in dollars per month. Which of the following defines C? So the devil is going to tempt you to say, the answer is A, because between 0 and 10, it's $75, and once you exceed 10, it's going to be an additional $5 more. But what this does is if I were to plug in 11, I would do 5 times 11 plus 75, which means 11 classes would cost like $100 and some dollars, and that's simply not true. What we have to choose is B, because B is saying that between 0 and 10, and including 10, it costs $75. But once you hit 11, you do 11 minus 10, which is 1, multiply that to 5, and then add 75. So 5 plus 75 is for 11, and 12 is going to be 10 plus 75, and so on and so forth. So kind of a tricky problem. Just, be really careful. This is a piecewise function. It's a calculator example, but I'm not going to use my calculator because the numbers seem to be friendly enough. The piecewise example says we're going to use this quadratic equation right here when x is in between -2 and 3. We're going to use this linear equation right here when x is in between 3, not including, and 10, not including. And the answer is going to be 5 if the x value is in between 10 and 12. So when f is 1, that applies to this scenario right here. So when f is 1 equals 9 times 1 minus 1 squared. 9 times 1 is 9. 1 squared is 1. The answer is 8. Easy peasy. When f is 10, that includes that guy right there. And when f is 10, no matter what, you're going to get 5. So f of 10 is 5. Hope this helps.